My name is Luis Castro, and this is the Traveling Salesman Problem. When planning a trip to St. Louis with numerous possible visits to locations around the city and surrounding area, we wish to get the most optimal travel route with the amount of time available. The problem is that there are multiple possibilities when planning routes, and finding the best option by hand is tedious and time-consuming. A Traveling Salesman Problem (TSP) optimization will provide the best route in the most efficient manner. Given a set of cities and distances between each pair of cities, the problem is to find the shortest possible route that visits every city exactly once and returns to the starting point. Like a TSP, the cities are broken into subgroups for multiple salesmen to travel to. This optimization will treat each location within St. Louis as a city, and each salesman has a different day of travel. Optimizations will be conducted with three sets of optimization criteria. The TSP was solved using a MATLAB code and an Excel file to keep track of locations that will be used. 16 locations were selected. Each location was given a ranking representing priority in visiting during the trip, a value for time desired at each location, and a ranking for priority for restaurants. Locations coordinates were found in Google Maps, assuming locations will be visited in a car, and that there are no traffic and routes provided are actual roads. The first optimization is a standard TSP optimization, finding the best route with 1, 2, 3, and 4 days of travel. No other criteria or constraints for this round of optimization. The standard TSP shows the optimal route. Each color on a multi-day TSP is a different route for each day. All 16 locations are visited. The second optimization is the TSP optimization with an additional time constraint. Each location is ranked on priority of importance of visiting. A desired time of stay at each location is given in minutes. A time limit for each day is set at 720 minutes. The solver will calculate the total time for all locations visited and will eliminate the lowest ranked location until the total time is less than or equal to the set time limit for each day. A comparison between the first and second optimization is shown. For the third optimization, in addition to previous constraint, solver will look for duplicate types of locations. Focus is on restaurant options. If a route has more than one restaurant on the route, then all other options are removed from the route. The restaurant with the highest rank stays in the route. After running the second optimization, all restaurant locations were eliminated due to previous ranking and time constraints. The following shows the optimization with just the multiple restaurants eliminated. The number of stops were reduced when a route had multiple restaurant stops. A comparison between the first and third optimization. A TSP solver allows for faster solving than a brute force method of solving. With 16 locations, the permutations for all possible routes from start and end point is 15 factorial, which is more than 1 trillion options. The MATLAB code created solves this in seconds, given the most optimal route along with additional criteria to further refine the optimization. Solver is not perfect as it is not considering actual roads, assumes no traffic conditions, and cannot account for any other outside factors. If the opportunity to continue working on this code were a possibility, the following would be done. Improving the code to run more efficiently, considering real-life conditions and roads, include time in traffic as part of the time constraint, and compare results to previously taken trip to see how a solver compares to the path taken by a person naturally.